general relativity step by step. I've got this beautiful expression for dust, for the stress energy tensor for dust. Dust is lots of particles which are so small you can ignore their internal structure. There's no stresses or anything to worry about, and they are at rest with respect to me. Or rest with respect to some rest frame. They're not moving relative to one another in inertial control volume. So I'm just going to play with this formula here, and of course what I'm going to do is to construct my friend Baz in his little spaceship here. There he is. That's Baz, and his ship is moving at speed u. And I've chosen units in which c equals 1, and we'll see what happens. So what's the fore velocity? Well, the fore velocity is going to be gamma, gamma u, gamma v, and gamma w, I guess. But because I'm just looking at one component which is going to be non-zero, it's going to be gamma, gamma u, 0 and 0. So what does the stress energy tensor look like for Baz? Well, I guess relative to him the particles are moving in with a negative velocity, but I'll just draw a veil over that. Rho 0, u alpha, u beta equals rho 0 times this great big matrix thing here, which is going to be gamma squared u, 0, 0, gamma squared u, gamma squared u squared, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Well, that's quite nice. I can factorize it out a bit more if I want. 0 gamma squared, so it's the energy density as measured by Baz, and then we're going to have a 1 u squared, and everything else is going to be 0. 0, 0, 0, 0, 0. That's fantastic, isn't it? So, a couple of observations. First of all, observe that stress energy tensor is symmetric. That's a general feature of stress energy tensors. The stress tensor in classical mechanics is symmetric, simply because angular momentum doesn't go to infinity as your control volume goes to 0. So that's a classical feature of stress tensors, at least. So that governs this 9 by 9 matrix down here. But it's true in general for all the terms of the stress energy tensor. The point I want to make about this is that if u is very, very small, slow, compared to c, I guess, compared with c, of course I'll set the speed of light equal to 1, then the stress energy tensor for Baz is going to be rho 0 gamma squared 1 u, and then 0, because if u is small, u squared is very small. So u might be 0.01, that's still quite quick by terrestrial standards, I guess. U squared is 0.001, is that right? No, there's another 0 there. That's 10 to the minus 2, and this is 10 to the minus 4, of course. 4, yes. So we can ignore terms of second order and above, that's why I wrote the 0 down there. 0, 0, 0, 0, 0, 0, 0, 0, 0. So we can see that this term here, so T 0, 1 is rho 0 gamma squared u, which is a flux. Which is showing that everything is checking out. This stress energy tensor here is doing what we want it to do. Yeah, we can also look at this component here, but we've got to, that's going to be the, ooh, I don't know why it does that. Just a minute. Get rid of those things. We can also look at this term here, which is going to be T, oh dear. What the? Sorry, my computer glitched out there. I'm talking about this. Oh dear. Yeah, I'm talking about this component here, which is T10, which is again rho 0 gamma squared u. but I'm going to re-bracket it. I'm going to say it's rho 0 gamma times gamma u. And you can see that that is a momentum density. It's actually an x momentum density. So we can see that this term and this term, it's symmetrical. It's not obviously symmetrical, but it is. It's one of these peculiar things where you just got to forget that one of your components is time. But stress, I'm going to write that out. Stress energy tensors are symmetric. It's a general feature of them. That means that T alpha beta equals T beta alpha. So for any rest frame and for any substance you can think of. Right, I'm going to stop there. Stop.